Hello.
Yes, ma'am.
Okay. Okay. I'm audible, right? Yeah.
Yes, ma'am.
And my
Audible, ma'am.
screen is visible.
Yes, ma'am. Visible, ma'am.
Okay. So we'll start and we'll wait for a few more people. We'll start at 5 and we'll start at 2 in 2 minutes.
Okay, ma'am. Okay.
Okay, we'll start. Good afternoon, everyone. I welcome you to the fifth problem-solving session of NPTL course Graph Theory. Last week we discussed matching in graphs, and in particular we were discussing matchings in bipartite graphs. So today's our problems will be focusing on matchings in general graph and stable matching problems. So let's begin. First of all, let's recall what is so this we also defined matching last time, but let's recall again. So matching is basically a set M of edges of G. So we have a simple graph. We have some graph G. Matching is a set of edges such that each vertex is adjacent to at most one edge in that matching set. And sometimes so and what is a perfect matching is a matching that cover all vertices of G. And sometimes perfect matching is also referred as one factor, and this one factor can be generalized to any positive integer. We say a k factor of a graph refers to basically a k regular subgraph of G which is containing all the vertices. So k factor should have two properties. K factor is a special type of subgraph of G which has two property. First of all, each of these vertices in that subgraph should have degree k, that is, it should be k regular, and moreover that subgraph should contain all the vertices of G. So now here are few examples. So you can see the first graph here. This is a bipartite graph, and the edges which are colored with green are matching. So matching was basically we have to find some set of edges such that set of edges, and each vertex could be adjacent to at most one of the vertex. So we see that this is some matching of this graph G. And similarly, if we look at this graph need not be a bipartite graph. uh, uh, so so we see that in this graph, all these green edges are matching, because in this case also all the edges or all the vertices are adjacent to at most one edge. So this, and moreover you can see this was not a perfect matching. In this bipartite graph, this matching which was M is equal to AD, BF and CG, this is not a perfect matching. Why it is not a perfect matching? Because it is not covering all the vertices. The vertex E is not matched in this particular matching, so this matching was not perfect. And now, but if we look at this matching, we can see that so what is this matching? So if I label these vertices also, 1 2 3 4 5 6 7, sorry, uh, is there any question? Okay. So if I label these vertices, so we see that in this particular graph, the matching that the green lines are forming, green edges are forming the matching. So edge 1, 2, 5, 6, 7, 8, and 4, 3. And this matching is perfect also. And therefore, this is also, as we have defined, it is also a one factor. Now, now now we see in the same graph, we can also have a two factor. So so these red edges are forming the two factor. So by two factor we means that each two factor means that so this subgraph of red edges form a two factor. Why? Because we can see all the vertices here have degree 2, and we also all the vertices are also covered by this. In particular, when you are looking for two factor, you are looking at, you want, when you want to find a two factor in graph, it is equivalent to find disjoint cycles in graph which are covering all union. So a two factor is basically a union of disjoint cycles in graph, because in cycle each vertex has degree true. It is a union of disjoint cycles in graph covering all the vertices. So first of all, so if a graph is Hamiltonian, can we guarantee that it will have a two factor? So it's a question. So if a graph is Hamiltonian, can we always find a two factor?
Yes, ma'am.
Why?
Because the cycle will contain all the vertices of that graph, ma'am.
Yes, yes, absolutely. So, so if a graph is Hamiltonian, that graph has a Hamiltonian cycle, and that cycle will cover all the vertices of the graph. So we see that Hamiltonian graphs always have a two factor. Now, now once we have defined what a matching and what a perfect matching is, we have a nice necessary and sufficient condition for a simple graph to have a perfect matching, which is as follows: that if we are given a simple graph, then this simple graph will have a perfect matching if and only if we consider any subset of vertices, the number of odd components in the graph when we subtract those vertices from the graph should be less than equal to the number of vertices that we have removed. So this is Toote's theorem. So you can see that this is so for bipartite graph also we had a necessary and sufficient condition. For a bipartite graph we had some necessary and sufficient condition to find appropriate matching. For general graph, Toote graphs gives a Toote's theorem gives us a criteria to say if a graph has perfect matching or not. So so in this particular example, suppose first of all we have seen that this graph has perfect matching. So this Toote's condition should be satisfied in this graph. So let's see first of all so it should be satisfied. Let's consider few examples of sets and see. So if I take my set S to be vertices B, G, and C. So if I removed these three vertices, can you tell me what will be the number of odd? So so Toote's condition is saying that if we are removing three vertices, then the number of connected component with odd vertices. C odd is basically counting the number of connected components with odd vertices. This number of connected component, they should be less than equal to 3. So in this case, is it true? So if our S is BGC, what is the number of what so if we remove these three vertices, what is the number of connected odd components? Odd connected components. Yeah. Did you understand the question? So basically basically what we are saying, so for this particular example, we have earlier shown that this graph has a perfect matching, and today's theorem says that G has a perfect matching if and only if we consider any subset of vertices, the number of odd connected components after removal of those vertices should be less than number of vertices that have been removed. So since this graph has a perfect matching, this two-taste condition should be satisfied. So if I am considering my S, so if I take any S, then the number of after removal, the number of odd components should be less than equal to the number of vertices that have been removed. So if I take my S to be BGC, what are the so first of all, if we are removing BGC, what are the connected components of the graph? So if I am removing BGC, I am left with this graph. A, D, E, F and H. Right? This is the graph that we are left with after removing BGC. So so in this graph, this is my G minus S. So in this graph, how many odd connected components are there? So we see this is one connected component and this is one connected component. Since this component has just have one vertex, so this is an odd component. But this vertex, this component has even number of vertices, so this is an even component. So for this S, C or G minus S is just 1 and this is less than equal to 3. So two-taste condition is satisfied. Now what about if I remove A, C, D, F. A, C, D, F. Now what is the number of connected components? Number of connected components and number of odd connected components. So is everyone understanding what are we
2,
doing?
ma'am. 2.
Yeah.
2.
Okay. So okay. So 2. What all components you are referring to?
B and H have odd vertices, ma'am. And
Okay.
G and E will be the another component with even number of vertices.
Yes. So if we remove these four vertices, you're saying right. So if we so the graph that we are left with is this, and we see that this is a odd component, this is a odd component. So number of odd components are 2. This is also one of the connected component, but it has 2 vertices. So this is the even component. So the number of odd connected components is 2. So we see that this this example was just to demonstrate what the C or G minus S mean. Now if we take this another example too, so if this is my graph, what do you think? Does this graph have a perfect matching? So we had a two-taste criteria. Two-taste criteria says that we should for all S, we should have C or G minus S. Number of odd connected components after removing those vertices should be less than equal to order of S. And if this condition, so today's theorem is saying if this condition is not satisfied for at least one set also, then that graph won't have a perfect matching.
So take S is equal to D.
Yes. Okay. If we take S equal to D, yes. Then what are the number of odd connected components?
3.
3. Yes. So if we take S equal to D, so basically if we remove this vertex. Sorry. So we are removing this vertex. So we see that what are the connected components that we are left with? We have this, and we have this. And all these connected components are odd. So we see that C odd G minus S is equal to 3. Therefore, this graph cannot have a perfect matching. This graph cannot have a perfect matching. So now we'll be doing some questions related to these only. So is the statement of two-test theorem clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay.
Ma'am, but I have one
Yes.
doubt in that two factor, ma'am.
Yes. Yes. Yeah.
Uh, the diagram contains two disjoint cycles which
Yes.
covers all the vertices. So
Yes.
that's why we are describing it as two factor.
Yes. Yeah. Yeah. So
If it has three cycle means then it is a three factor like that, ma'am.
no, 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 no. Two.
Oh,
This two. So see. So we showed that. So this Hamilton. So if we look at this graph also, if we are just taking this graph, suppose this K3. This is itself. This is a cycle. This is itself a two factor. So this here two is coming from the degree of vertex in degree of each vertex in subgraph. So since degree of each vertex in degree of vertex in each cycle is 2, therefore it is a two factor. So basically when we are looking for k factor, so when we are looking for k factor in a graph, we are looking at a subgraph which is k regular, that is all the vertices should have degree k. So now we can see by two factor. So by definition, if we want to find a two factor, we are looking for finding a subgraph in which each vertex has degree 2, and you can think about it that finding a subgraph in which each vertex has degree 2 and all the vertices should be covered 2. So any simple graph in which each vertex has degree 2 has to be a cycle. Therefore, in the
okay,
case,
ma'am. Understand, ma'am. Thank you.
yeah, okay. Now we have this. So yes, so now we have this graph. Now in this graph we'll see again what these two factor mean. So the first question is, we have to find one factor, two factor and three factor in this following in the same graph, in this graph, if it exists. So first of all, what is a one factor? By one factor we means that we want to find a one factor is equivalent to find a perfect matching. So does this graph has a perfect matching? So the question is that we are given this graph G. So we have to find two things. A part is to find one factor, B part is to find a two factor, and C part is to find a three factor if exists. So one factor by definition is same as a perfect matching. So if you want to
No,
find,
no,
yeah,
not perfect matching.
huh?
We can't find perfect. We can't find perfect. Perfect matching it is.
Oh, so you are saying perfect matching does not exist for this graph?
Exist.
It exists.
Yeah.
Yes. Okay. So kids, so what is the perfect matching for this?
AC,
Okay. Wait. Yeah. AC. Yes.
PG,
BG.
CG.
CG.
Hmm.
So if you want to find a perfect matching, each vertex should be at each vertex should be adjacent to at most one edge. So now you have chosen your edge AC. So you can't choose CG, right?
Okay. So CI.
You now once you have chosen AC,
Hmm.
once you have chosen AC,
Uh,
you can't choose any edge
not
with.
EG, I think so. That.
Okay, yeah, EG you can take,
Mhm.
yes.
Yeah. Then DB,
DB, okay.
WF,
W.
no,
Okay,
G
H. Okay,
adjacent.
this is H. Okay, you HF.
Okay. And IJ.
Yes, very good. Yes, this is right. So this graph had 1 2 3 4 5 6. this graph had 10 vertices. This graph had 10 vertices. So if you want to find a perfect matching, you have to find 5 edges. So he has given us 5 edges, and they are also covering all the vertices. So this is a perfect matching. So does everyone agree? So this is a perfect matching?
Yes, ma'am.
Okay. So now once we have found a one factor, now the B part is to find a two factor. So as I have told you earlier, two factor is basically same as finding
Two
two
disjoint cycles.
yes, disjoint cycles, not necessarily two.
Yeah, we can
Disjoint
find.
cycles, disjoint cycles covering all the vertices.
Yes, we can find.
Okay. Okay. So what is a two factor in this graph?
ACGIEA. One
uh
cycle.
A C
GIEA.
G I. Okay, so you are saying this one. Yes.
Same way
Okay.
the other side.
Okay.
DB. BD.
Okay. Yes. So see, in this it has given we a disjoint cycle. It is a so we have two cycles which are covering all these vertices. So this is one of the two factor. Can anybody give some other two factor for this graph? Can anybody else give some other two factor in this graph? This is fine. This is one of the two factors. But does this graph any does this
Ma'am.
graph different? Yeah.
Ma'am. ABJI.
Wait. ABJI. Okay. ABJI.
Next one.
Yes. Next.
E ECDFWG.
Okay. ECEFWG. Yeah. So this is also a valid two cycle. A valid two factor. Good. So does everyone understand what a two fact at least what a one factor and what two factors are? Okay. So we are getting two examples, and there are many more. Red and blue are two factors. Now the C part is to find a three factor. So now this is a bit tricky one. So we have to find a three factor. So what do we mean by three factor? We want to find a subgraph of G such that all vertices subgraph of we want to find H, which is a subgraph of G such that all vertices have degree 3 and all the vertices are there. So now first of all, like if you want to find a three factor here, first of all we can observe that so basically all the vertices have degree 3. So if you want to find a three factors, then from each vertex we have to choose for each vertex we have to choose kind of a three edges. So first of all, let's see what is the degree count of this graph. So in this case we can see all the vertices are have degree 4. So all the vertices in this graph you can see have degree 4. Now we want to find a three factor basically. So we want to find a subgraph in which each vertex has degree 3. So basically we are allowed to remove at most one vertex. We can remove at most one edge. So in our subgraph for each vertices we have to include 3 edges. So degree of each vertex is 4 and we want degree to be 3.
We can miss.
Yeah.
We can know in
Yes.
this graph.
Yes. Also, yes, we can do so. So you see that first of all, degree of each vertex is 4, and we want degree to be 3. So this graph had a perfect matching. So in perfect matching, degree of each vertex was 1. So in this special case we can see that since this graph is 4 regular, complement of matching complement of matching will give us a 3 factor. So 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 our matching was this. So if we so we have complement of perfect matching. So our matching was basically this. Now if we look at the complement of this graph, complement of this perfect matching, so basically this purple thing, we'll see that we have found a 3 factor. Why is that? Because so we are taking the complement of our perfect matching. So in perfect matching, each vertex has degree 1. So now we are removing each vertex has degree 1. So when we are taking complement, we are removing all those edges in the perfect matching. So we are removing one. So for each vertex we are removing one edge which is adjacent to it, exactly one edge. So we are left with 3 edges. Okay, so okay, wait, this was not the perfect matching. I This edge was not, this is purple. So you see the graph which is in purple is a 3 factor. This graph which is in purple is a 3 factor.
So does this mean, ma'am, that a graph to have a three factor, it should be one factor first?
Huh? What are you saying?
The graph to be a three factor, whether
Yes.
it should be a one factor necessary condition.
No. I'm just saying for this special case, since this so for K, basically for K, you can generalize this for K regular graph. So if you have a so if you have a K if you have a K regular graph, then and it K regular graph with a perfect matching M, then M complement in G will give you a K minus 1 factor. So since this particular graph was 4 regular, so this particular graph was 4 regular, so the complement of perfect matching here is giving us a 3 factor. So is everyone convinced why this is true, that if we have a K regular graph, then and K regular graph which has a perfect matching M, then if we'll take its complement, it will give us a K minus 1 factor. Why? Because what is a K minus 1 factor? It is a subgraph of G. It is a subgraph of G where each vertex has degree k minus 1. Degree k minus 1 in that subgraph. And so in this case only you can see that this purple graph is giving us a giving us a three factor. Why? Because so first of all, this graph is this purple subgraph is covering all the vertices, and if you look at the degree of each vertex, in this purple graph, it is coming out to be 3. So degree of A is 3 because this edge AI, AE, AB, each each vertex has degree 3 in this purple graph. So this is indeed a 3 factor. So is everyone okay with this?
Ma'am, I have one doubt, ma'am.
Yes, yes, yeah.
Here we are, you are saying that the graph is a three factor by taking a complement to that perfect matching.
Perfect matching in that graph itself. Basically, we are remove in complement in by complement by in that in G. So basically,
Yes, ma'am.
G we are talking about G minus M. Yeah.
Yes, ma'am. Yes, ma'am.
Yes.
Uh, so we can call that G has a three factor.
Yes. Yes.
If the complement of the matching perfect matching is a three factor, then the graph itself will be called as a three factor like that. Yes, ma'am.
Sorry. Repeat your question again. Yeah.
Ma'am, whether the G minus M is a three factor
Hmm.
or if the graph with perfect matching, you are taking
Huh.
the graph with the perfect matching.
In the yes, but this yeah. So this is a very so in this example only it is coming out to be because this is a four. So I'm just saying that if we have a four regular graph,
Yes, ma'am.
by four regular graph we means that each vertex has degree 4. So G is a four regular graph. So if we take G minus perfect matching, the graph this graph, G minus
Yes, ma'am.
perfect matching, this is a three factor.
Okay, ma'am. That's my doubt, ma'am.
Yeah.
But we don't call G as a three factor.
No, no.
Okay, ma'am.
No,
Yeah.
madam.
Yeah.
Hello.
Yes. Yeah.
Hello, ma'am. You are confusing us because you are on
Yes.
one side you said it is a
Yes.
special case for four regular, and on the other side you are saying for k regular graph.
Yeah. Yes. So, but that
So,
is
so
also
it is
like
not a, so for k regular it is not a special case. So it is generalized.
yeah, yes, yes, but like so regular graph, k regular graphs are also a special case, right? Simple graph need not be a k regular. So this regular graphs are a special case. So this is not. So I'm just saying that this is not true for a general graph. That if you are given a general graph and if you take complement of perfect matching, then it will not give you a three factor or some. It is not necessary that complement of perfect matching in a simple graph is a k factor. Only in this particular example. So by in this particular example, since this graph was 4 regular, the complement of perfect matching was coming out to be complement of perfect matching was coming out to be a 3 factor. And now this example can be generalized to a special case of k regular graphs, that if you have a k regular graph, then the complement of perfect matching will give you a k minus 1 factor. I'm just saying this.
Okay.
So is the confusion is the confusion still there?
M complement and G minus M is same. You mean to say
Uh,
M complement and G minus M is same. You want to
they,
say?
so I'm saying complement of so the complement is just a set theoretic term. So we have a complement of a graph that is different. So here I'm just saying G minus. So no, complement was a wrong.
Ah,
By complement I mean just that I am removing the edges in M.
oh, that's
Okay, yeah.
it is not a complement of M.
Yeah. So this complement is not the complement that we yeah, this m complement in G basically, that means just G minus n.
Yeah, it is
Yeah,
G minus M,
same.
not M complement.
Huh. Yeah, okay. Yeah. Yeah. Okay. Any other questions regarding this?
No, ma'am.
Okay. Okay. Now, next question is, so using the two-taste criteria, we have to show if these graph have perfect matching or not. So our first graph is this. So what do you think? Does this graph have a perfect matching? So basically, we have to look at the two-taste criteria, which says that C odd G minus S should be less than equal to order of S. So this is our G. So what? So does this graph has a perfect matching?
No, ma'am.
Okay. What? So no. Why?
Because we can't cover all the vertices by um, taking that vertices, considering the vertices at once, ma'am.
Uh. Okay. Why can't we
Because
cover? Yes. Why
if
can't?
the yes, ma'am, here if the edge 5 and 5 6 is covered means then the fourth will not be taken in that cover, ma'am.
Yes. Okay.
5 and 6 if we take that in
Hmm.
that matching,
Hmm. Hmm.
then the 4 will be leaved as
Okay.
single, and also in that 1 and 3
Yeah.
you cannot take 2 in that matching cover, ma'am.
Okay. Yeah. Okay. This is so you are saying base. So yeah, like this is intuition is right, but if we want to show this using two-taste criteria, that if we want to find some set S, so you are basically saying that 5 6 and 6 4 so if we are including any, so so what you're saying is right. So you're basically saying that if you are including any one edge corresponding to 6, many other vertices will be left out. So
Yes, ma'am. Yes, ma'am.
so intuition is right, but like if you want to prove it, so what you say, so you are, so you looked at this six vertexes might create some problems. So what you do is you first try to take your S to be 6 and then see what is the C or G minus S is coming. So if we remove 6, how many odd components will we have? If we remove 6, how many odd components will this graph have?
Two,
Yes. So
one, one, two, three.
this, so how many odd components it will have? 3, right?
3, ma'am. 3.
3.
Yes, ma'am. 7, 8, 5, and 1, 3,
Yes.
2, and the 4.
Yes. So G minus 6 is this. So this is coming out to be 3. So this condition is not satisfied. So from Tute's criteria, we can say that this graph cannot have a perfect matching. So what you were saying is also correct, that if you are including any edge 6, so this is happening because of this condition which is failing. So now what about this second graph? What do you think? Does this graph has a perfect
And
matching?
can you modify this first graph by adding a loop and parallel edges in the first graph? If you add some loop on vertex 1
Okay, wait.
and parallel edge on vertex 8 5,
Okay, wait. So you are saying a loop here.
loop and parallel edge on vertex on edge 8 5,
Yes, okay.
and and then what will happen?
Okay. Uh so so first, Okay, so we are adding an additional edge. So then also, if you see, if you are removing 6,
Mm.
if you are removing 6, then also the number of odd components is not changing, right? Because by odd components we mean that the number of vertices should be odd. So if you are adding some more edges, and if you remove again this 6, so now the subgraph is again this 5 8 7 1 3 2 and 4. So now again, if you apply this two taste criteria, so you are getting that. So if you apply two taste criteria, this is two taste criteria is not satisfied after adding this also, then so this graph, after this graph won't have a perfect matching after, like, your new graph won't have a perfect matching either. Is that fine?
Is here one, two, three become even component?
No, no.
No,
By
it is
odd,
three.
yeah, number of vertices are still 3, right?
Number of vertices are three,
Hmm.
but the degree is six, no?
Huh.
In
But
the
by odd component we means that number of vertices are odd. And I think, oh, also the two taste
number of vertices.
yeah.
If you take loop as one vertex,
Hmm.
then the number of vertices will be four, no? In in one, two, three.
uh, no, number of vertices is
It is
still,
not.
number of vertices is still 3. Also, I think the two taste criteria was for simple graph.
Okay.
Huh.
So no loops will be there in simple graph.
Yes, yes. And no parallel edges also. Two taste criteria was for simple graph. Like, but still,
No,
like,
if
but
we
it
do
was
not
with,
apply the,
but if even
if
if
it,
we don't apply two taste
uh,
criteria, then also
uh,
this graph won't have a perfect matching by the same argument. So if you see that, so if we are, so basically if we are removing 6, we are resulting in 3 odd components. Now if we want to construct, if we want to, now this is, so if we want to construct a perfect matching,
mm,
so if we want to if we want to construct a perfect matching, first of all we see, so since this is, so these are the components and this is 6. So if we want to construct a perfect matching, 6 4 should be there, because, so let's try to construct a perfect 6 4 should be there in the matching, because 4 has just one edge incident to it. So if a
mm,
perfect matching is there, 6 4 should be there. So this is there, but now if 6 4 is there,
mm,
but now if 6 4 is there, so now if we want, so 5 6 cannot be there, so either, so if 6 4 is, so 6 4 is there, then this 7 7 6 cannot be there, so the next edge in perfect matching would have to be 7 8, right? So
mm,
this should be, this should be there for sure, and 7 8
mm,
should be there also for sure.
yeah.
Now 7 8 is there. Now you see there is no vertex. Now we cannot cover this vertex 5 with any of the edge, right? So if
Three one, 3 1. Can you connect 3 1?
we can connect 3 1, yes, but we won't get perfect matching, because in any of the matching 5 won't be covered. So if this graph has a
Oh.
perfect matching, 5 should be covered, right?
Mm-hmm.
So this graph won't have a perfect matching.
Okay.
Okay, so now next problem is this. So what do you think? Does this graph has a perfect matching? This is K5. Does this graph has a perfect matching? This second example.
No, ma'am.
Okay, why?
Because odd number of vertices are there.
Yes, yes, nice. So, so, okay, sorry. So, since this graph has odd number of vertices, perfect matching cannot be there because this is a simple graph, and if it has odd number of vertices, then this graph cannot have a perfect matching because in any of the matching, matching is basic. If we have a matching, we are basically constructing disjoint union of edges. So if we are considering any matching, one vertex will always be left out. Therefore this graph cannot have a perfect matching. So any simple graph with odd number of vertices cannot have a perfect matching. So is this fine with everyone? So also, but if you see, so but if
So
you
this
would,
rule can be applied to the first example. This odd number of vertices, this criteria can
huh,
be applied to our first example.
but in the first example we have even number of vertices. We have 8 vertices.
8 verses.
Hmm.
Yes, odd number. Okay.
Yeah. Yeah, so yeah, you are right. So if a graph has odd number of vertices, you don't have to check anything. You can directly
Okay.
say that this graph cannot have a perfect matching. Because then your so for that case you can just take your S to be empty. So order S is 0, but number of odd components is 1. So you see, if a graph has odd number of vertices, by two-taste criteria, so we have so if a graph has odd number of vertices, we have a logical explanation also why it cannot have a perfect matching for a simple graph, because in any matching we'll have even number of vertices. But if you want to show, like, but two-taste criteria was a if and only if condition. So for it should, so a graph with odd vertices not having a perfect matching should also be reflected in two-taste criteria also. So it is reflected by taking your S as empty set. So if you take your S to be empty, if you take your S to be empty, order S is 0, but C odd is 1. So you see that if a graph has odd number of vertices, two-taste criteria is not satisfied for this particular set, and therefore this graph cannot have a perfect matching. So you have two reasons. So is this question clear to everybody?
Yes, ma'am.
Okay.
Ma'am, in that second graph, if we take S as D, set
Yes.
S as only D,
Yes.
then we will have the graph as AC, A, B, C, and E,
Hmm.
and it is a three factor, right, ma'am?
Uh, which is a three factor? What is a three factor? A-
A, B, C, and E. If you remove the vertex D from E,
Okay, if we
from
remove,
G,
yeah, if we remove the vertex G from, if you remove the vertex D from G, oh sorry,
yes,
yes, okay, then you are
then it is
saying,
a three factor,
why,
right, ma'am?
why, why is it a three factor?
Because we are getting a subgraph
Hmm.
with all vertices of degree 3.
But what about D?
Oh, ma'am, we are not including that in G, ma'am. Okay, ma'am.
Oh no, but
We are G minus S.
yes,
That's S includes the only the vertex D.
yeah, yes, but three factor is, so oh you are saying this graph. So
Yes,
G
ma'am.
G does not have, so if you consider K5, if you just consider K5, so I'm saying this subgraph is not a K5, this subgraph is not a three factor of K5, but it is a three, but if you are taking your G as this is a three regular graph, so it is so so it is a trivial, so 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 when you are taking G minus S, you are getting this is a three regular graph. So this is a
Yes.
so this is a three, three factor, but basically when we are talking about k factor, we are talking about subgraphs.
Yes, ma'am.
So
Oh, it should include
this
all
is, yes,
vertices.
yes,
Okay.
yes. So
Okay,
so
ma'am.
k5 so this is so your g minus s, your g minus d is not a three factor for k5.
Okay, ma'am. Okay, ma'am. Now it's
Yes.
clear, ma'am. Thank you.
Oh, yeah. Okay, so
Ma'am,
yes, yes, there's a question.
example, if it first example, is it perfect matching, ma'am?
uh so yes, we showed that the in this first you are saying about g, right? uh the first example we showed that this does not have a perfect matching by Tute's criteria. So if basically if I'm just getting back to my original example, so we did not have this edge, so we did not have this edge. Yeah, so this was my first example, this was our first example. So we are saying that this graph does not have a perfect matching, because if I take my s to be just 6, then if I take my s to be 6, then what is g minus s? G minus s is this graph, basically this graph. G minus s was coming out to be this graph, which has three odd components, which has three odd connected components. But Tute's
Yes, ma'am.
criteria says that the number of connected odd components after removing three vertices should be less than equal to less than uh, uh, so we are removing one vertex, so the number of odd connected components should be less than equal to 1, but we are getting three odd components. So Tute's criteria is not satisfied, hence this graph cannot have a perfect matching.
Okay, ma'am. Thank you, ma'am.
Yes, yes. And moreover, also this second graph also does not have a perfect matching because it has odd number of vertices. So in this second question, both g and k5 does not have a perfect matching. Okay, so now let's move to next question. So now next is the stable matching problem or stable marriage problem. So the stable marriage problem is this. We are giving we have two set of data. We have list of men and women, and plus we also have their preferences. So we have a list of men and women. So this is a list of men. So we have four men and four women, and and the and they have listed down women in the order of their preferences, and women have listed down the men in the order of their preferences. So now the question is to find a stable matching for this data. So first of all, what do we mean by stable matching? First of all, what is a matching? Matching is basically a 1-1 correspondence between these two sets, which is the set of men and set of women. So basically we are looking for a 1-1 correspondence between men and women. Basic, that is, we are assigning to each men, we are assigning one women to each man, and all these and all these are distinct. So by 1-1 correspondence we mean that by 1-1 correspondence we mean that all these women should be assigned to some men. Moreover, one man cannot be assigned same women. So this is what do we mean by matching. So in this case, you see, so if this is our list of men preferences and this is the list of women's preferences, the two sets are set of men and set of women. So in this case, m1w2, m1w2, m2w3, M3W1 and M4W4 is a example of matching, because so m1 is assigned w2, m2 is assigned w3, m3 is assigned w1, and m4 is assigned w4. So why it is a matching? It should be a 1-1 correspondence. So each man has been assigned some women, and all the women's also, each woman has been assigned some men, and no two women are assigned to same men. So we see that this is a matching. So this is what we mean by matching. But the question is to find a stable matching. So what do we mean by stable matching? So before defining stable matching, I want to define what is a blocking pair for a given matching. So if this is my matching M, I will say that MIWJ. MIWJ is a blocking pair for this particular matching. If this, first of all, if this pair is not an element in M, and moreover, so if M is a matching, mi has been assigned some women, say W, and wj is also assigned some men, which is M. So now this will be a blocking pair. This will be a blocking pair for M if and only if that mi will prefer wj over w, and wj will prefer m over mi. So what do we mean by that? Mi prefers wj over w. Mi prefers wj over w. We means that if we look at the list of preferences of mi, then wj has a better preference. So in this case, suppose m1, so so we can say that m1 prefers w2 over w4, because w2 in the line of m1, w2 is appearing first. So when we say somebody, so whichever women are appearing first in the list are preferred more. So this is what we call a blocking pair. So let's see an example of a blocking pair. So suppose we have the same list of data. So we have four men and four women and their list of preferences, and we are considering this matching. So basically m1 is assigned w2, m2 is assigned w3, m3 is assigned w1, and m4 is assigned w4. And in the women's preference also we reverse. So w2 has been assigned to m1, w1 has been assigned m3, and m3 has been assigned w1. So we see that this is the matching. Now we want to see that if this matching has some blocking pair or not. So first we consider m3w2. So now if we look at m3w2, so in m3 has been assigned w1, but m3 has been assigned w1, but m3 prefers w2 over w1. So first condition is satisfied, that m3 prefers w2 over w1. And second, we also, so to have the blocking pair, both men and women should prefer this. So now, and w2, now if you look at w2 has been assigned m1, but w2 prefers m3 is coming first, m3 is coming for before in the list, before m1. So w2 prefers m3 over m1. So we see that this pair, so if this pair is a blocking pair for this pair is a blocking pair for M, because they are better. This M3 is also preferring W2 over the person that he has been assigned, and W2 is also preferring the person that has been assigned. So is the definition of blocking pair clear to everybody? So if we are given a matching, and what is a blocking pair, is it clear to everybody, the definition, or is there any confusion?
Please tell me.
Sorry, yeah. Yeah, So I'll explain again. If I think you just said that. So I am considering this as my matching. This is my matching. That is, M1 is assigned W2, M2 is assigned W3, M3 is assigned W1, and M4 is assigned W4. And now I want to see if this M3 W2 is a blocking pair for this matching. So M3 W2 will be a blocking pair for matching. So here also you see, so we saw M3 W2. So M3 W2, M3 is assigned W1, but he prefers W2 over W1. And similarly, W2 is assigned M1, but she prefers M3 over M1. So we see that M3 W2 is a better pair in the matching. Therefore, it is a blocking pair. Now is the definition clear? And similarly, you see that M3W3 is also a blocking pair. So why M3W3 is a blocking pair? So W3 appears, so M3 is assigned W1, which, but W3 appears before W1, and so M3 W3. Now if we want to look at for W3, also W3 has been assigned M2, but M3 is appearing before M2. Therefore, both M3 and W3, both M3 and W3 are better off with each other than the person they are assigned previously. Therefore, it is a blocking pair. Is the definition of blocking pair clear?
So, ma'am, we have to check for each pair apart from matching, no?
Yeah. Oh, yes. Yes. I'm defining what is a stable matching after that. But first, yes. So, so this first, this was just the definition of blocking pair, and a matching will be called stable matching if there are no blocking pairs. So, if a matching even if a matching has even one blocking pair, then we'll call that matching to be unstable. But to show that matching is stable, there should be no blocking pairs. So now once we, so okay, let's do it with an example. I think that will be better.
M3W2 is not a blocking. M3W2 is a stable matching because both are preferred.
No, no,
M3W2.
no. I'm saying M3W2 is a blocking pair for M, because
Or
M. So we have this matching M. So we have so this is a matching that has been given to us: M1W2, M2W3, M3W1, and M4W4. So this is a matching. Matching is basically so when you are saying matching, you are assigning one man to each woman and one woman is assigned to each man. So this is a matching. Now blocking pair is just one pair or one tuple. So M3W2 is a blocking pair for this matching because M3 will be happy with W2. Like M3, M3 has been assigned this W1, but M3 prefers W2. And this is happening for W2 also. So for this to have a blocking pair, both M3 and W2 should be happy. It's not that only one is happy. For saying that it is a blocking pair, both should be better off.
yes, yes.
So now if you see M1W4, M1W4, so you see W4, M1W4 is not a blocking pair. M1W4 is not a blocking pair because if you see W4 is W4 is assigned M4, but W4 will be happy with M1. But M1 is assigned W2, M1 won't be happy with W4. So for this, for a pair to be a blocking pair, both should be happy. So in this case, only W4 is happy. Therefore, this is not a blocking pair. Okay, we'll look at more to get it more clear. We'll look at more examples. So first of all, matching is basically a 1-1 correspondence between men and women. So basically, each man has to be assigned a woman, and each woman has to be assigned some men. So matching is these four. Matching is a collection. If there are four men and four women, matching is collection of four assignments, four tuples. A blocking pair is just one tuple in which both in which I have just defined. Now if I consider this different matching, so now I am considering this as my matching. M1 is M1 W1, M1 is assigned W1, M2 is assigned W3, M3 is assigned W2, and M4 is assigned W4. And similarly, so and women's, and this is the women's, this is same matching in the women's list, that M1 is assigned W1, W1 is assigned M1. Now we want to see if M1 W2 is a blocking pair. So for this example, what do you think? Is M1 W2 a blocking pair? So
No.
M1 W2 is a blocking pair. No. Why?
The W2, the W2's reference is M3 over M1.
Yes. So W2 is assigned M3,
M3 over
M3,
M1.
but is assigned M3. So W2 prefers M3 over M1. So M1 W2 is not a blocking pair, right?
Yeah.
What about M1 W4?
Yes, it's a blocking.
What?
Yes, it is blocking.
Yes, M1. Why M1 W4 is a blocking pair? So we see. So M1
Because
W4 is this. So M1 is happy, and W4 M1, W4 is also happy. So both are happy. Therefore M1 W4 is a blocking pair. Yes, and M1 W2 is not a blocker. Okay. So now if we consider this example, now we are considering this matching M1
Excuse me,
W.
ma'am.
Yes. Yeah.
In previous example,
Yes.
it's no meaning by taking that other pairs, no? M2W1, M2W4,
Yes, yes,
like that.
yes. I'm coming to that only. Why I was coming. So if we want to see, some match, if some matching is stable or not. So we have to see that if we can find better pairs or not. So it is sufficient to consider just these two pairs, because pairs after that. So if you see all the pairs after these red circles, these won't be better off for the men, right? So if we take any pair here, so suppose I am taking M3W1, and this won't be a blocking pair because M, M, M3 will always prefer W2 over W1. So it is sufficient to check blockingness for just these two pairs to see if this matching is stable or not. So we'll see in this next example only. So first of all, this is my example 3. Now we want to see if this is a stable matching or not. So suppose first of all, consider this pair M1W2. What do you think? Is M1W2 a blocking pair? Is
No,
M1W2 a blocking pair?
no, ma'am.
No, ma'am. No, ma'am.
Okay, so M1 will be happy with W2, but we see that W2 won't be happy with M1. So it is not a blocking pair. And what about M4W4? Is
No,
M4W4 a blocking pair?
no, because W4 prefers M1 over M4.
Yes, because W4 prefers M1 over M4.
M4.
Yes. So it is also not a blocking pair. So we see that this is not a blocking pair, this is not a blocking pair. So now can we conclude that this matching won't have any blocking pair? Because we have checked for this, and all these pairs that we are, so we can see that if we look at this M1W1, this M1W1, so M1 won't be happy with M1W1, right? Because M1 obviously prefers W4 M1. Similarly, M1W3, M1 won't be happy with W3 either. So we see all these preferences after their preferences, they won't be a blocking pair. So we see that we have no blocking pairs for this matching. So therefore this matching is stable. M double prime is stable matching. So is everyone convinced why M double prime is stable matching? Or are there any doubts? I can repeat it. If a definition of blocking pair is not clear, or if definition of stable matching is not clear.
Ma'am, always matching man woman is written. Yeah, sometimes woman man is also taken.
Sorry, sorry.
In a matchings, no, in examples,
Yeah.
whatever I saw in the videos and these,
Yes.
we took man woman.
Yes.
Other woman man also matching problems are there.
Yes. Yes. So see, the this was like, so
Optimal. Here, man, woman man is optimal.
sorry.
Men's table is optimal, no?
No, but you can consider women oriented matchings also.
Yeah.
So we'll
Imagine.
see, we'll have now, like in other, like in later questions, we'll see, we'll be finding a stable matching from the given data. So it is upon us if we want to choose, like if we like, it will be mentioned whether we want a men oriented matching or a women oriented matching. So if we want a men oriented matching, we start with men, but we can also have a women oriented matching also. So we'll see. So what was your was this your question that is like,
But in practice, it is always on man oriented.
sorry, what are you saying?
In practical life, it is always man oriented, no?
Okay. In not necessarily. Yeah.
I'm joking.
Okay. Yeah. Uh, Now, okay. So now this is our next question. So we want to see if this is so our question is like, it is similar to our example. We want to see if this matching is a stable matching. So let's see. So first of all, what is this matching? M1 is assigned W4. M1 is assigned W4 and W4 is assigned M1. M2 is assigned W3 and W3 is assigned M2. M3 is assigned W1 and W1 is assigned M3 and M4 is assigned W2 and W2 is assigned M4. So what do you think? Is this a stable matching? So so if you want to find some blocking pairs, they are lying somewhere here or here. So if you want to find blocking pairs, so if you want to check if it is has have a blocking pair, so either you want to check all these pairs or you want to check these pairs. So if there is any blocking pair, they are lying in this green area.
M2W4,
Uh, okay.
M2W4, one of the blocking pair.
M2W4. Yes, you see W4 prefers M2 and M2 also prefer W2. So M2W4 is a blocking pair. Therefore, this is not a matching. So let's see. So what about M1W1? Is M1W1 a blocking pair?
No,
No. Why? Because so M1W1 is not a blocking pair.
it
M1,
won't be the blocking pair on because
yes,
W1's preference is no, no, no.
yes, M1W1 is not a blocking pair. That's right.
Because W1 prefers M3 over M1.
M1. Yes. Yes, that's right. So, so basically, to show that it is not a stable matching, it is enough to find one blocking pair. And since you have found a blocking pair, therefore, this is not a stable matching. but it's just like to have more practice, like let's see or two more pairs to see if we have completely understood the definition of blocking pair. So what about M3W2? Is M3W2 a blocking pair?
No,
No.
ma'am.
No, ma'am. No, ma'am.
M3, so M3W2. Yes, M3W2 is not a blocking pair because W2 prefers M4
M4.
over over M3. Okay. So
M1W3 is a blocking pair.
uh M1
M1W W3.
M1W3. Yes, M2W4 is a blocking pair and M1W3 is also a blocking pair. Right. So yeah. So now is this fine with everyone? Definition of blocking pairs and whether now is the now the first part of thing is clear, that if you are given a matching, if you want to see if this matching is stable or not. Definition of blocking pair and if there is any confusion in definition of blocking pair or definition of stable matching, you can ask. Okay. Okay. So before moving on to find the stable matching, let's look one more example. So we have this. So now we have basically three so ABC can be referred as men and XYZ are women, and we want to see that if these are stable matching or not. So first of all, this AY, oh sorry, AYBZCX. So this is YAZB. So is this a stable matching?
Yes, ma'am.
Yes, yes. Because you see, this everyone is in men's side. Everyone is getting their first preferences. So all the other pairs won't be preferable to men. So this is a stable matching, and you also can see that this is a stable matching which is men oriented. Now what about M3? M3 is AZ, BX and CY. So AZ, BX, CY. So what do you think about M3? Is M3 a stable matching or not?
Yes.
Yes, ma'am.
Yes, because all we can see that all those other pairs won't be preferred by women. So this is a women oriented stable matching. Now we have M2. So in M2, like, okay, M2 is this AX, BY, CZ, XA, YB, ZC. So what do you think about M2? Is M2 a stable matching?
No, ma'am.
Okay, why? So if you're saying that M2 is not a stable matching, you'll have to give me a blocking pair. So is there any blocking pair?
X XV.
Huh? Sorry.
Uh,
So this is the we are considering M2, the black one now.
uh,
So ignore the green and blue
Stable,
ones.
stable.
Is M2 a stable matching?
Think
no,
so. Stable.
So if you have to check that, we basically
it's not stable matching. MP is not stable matching
yes. Why? Because suppose,
because
see, we have to
A
check.
prefers
We have
A
to.
prefers X, but X prefers uh, A second one. X prefers B first.
Yes. So if we want to show that this is a stable matching, We have to see that all these three pairs, they are not blocking pairs. We know that these three cannot be blocking pairs. We just need to check for these three. So we see that ay is not a blocking pair. Ay is not a blocking pair because y prefers b over a. Even bz is not a blocking pair and cx is not a blocking pair. So we see that this matching M2 does not have any blocking pair, therefore it is a stable matching. So is this question clear? In this all these three matchings are stable. Is it clear? So for M1 and M3 it was clearly visible that they are stable matching. For M2 we have to check that if they have no blocking pair. So for M2 also, is it clear? Sorry,
Ma'am, again explain, madam.
which part? B part?
M2, M2.
M2. Okay, yes. So let's this is a bit messy, so I'll draw again. A B C Y Z X X Y Z Z X Y, and this is X Y Z B C A B C C A B. So we are considering this following matching. A is assigned X, B is assigned Y, C is assigned Z, X is assigned A, Y is assigned B, and Z is assigned C. So this matching M2 we are considering. So now to see that if it is a stable matching, we have to show that this matching does not have any blocking pair. So first of all, if we are looking at this, so we see that AZ, AX and AY, they are not blocking pairs. So these three cannot be blocking pairs. Basically AZ sorry AZ, BX and AZ, BX and CY, they are not blocking pairs. Is this fine with everyone? Why they are not blocking pairs? Because you see, if AZ is not a blocking pair because A prefers X over Z. BX is not a blocking pair because B prefers Y over X. And CY is also not a blocking pair because C prefers Z over Y. So both A, B and in all these cases A, B, C are happy with their assigned choices than these ones. Therefore they are not blocking pairs. And similarly you can see that AY, BZ and CX, they are also not blocking pairs. So AY, if you look at AY, Y is preferring, so if you look at this AY, BZ, CX, they are appearing here. And women are happy with their assigned choices rather than these choices. So therefore these are also not blocking pair. So if you look at particular for AY, Y prefers B over A. So it is not a blocking pair. If you look at BZ, Z prefers C over B. So BZ is not a blocking pair. And if you look at CX, X prefers A over C. Therefore this is also not a blocking pair. So this is a matching which has no blocking pairs. Therefore this matching is a stable matching. Is this clear? M2 has no blocking pairs.
Yes, ma'am.
Therefore no stable matching.
But
Applicable.
man-oriented stable matching is M1, isn't it?
So
Hello, ma'am.
stable matchings are not unique.
Okay.
All three of them are stable matchings. Stable matching need not be unique.
Okay, but man-oriented stable matching is only M1, no?
Uh,
Man-oriented stable matching is only M1.
yes, if we start with men, yes, yes, in that algorithm, like if you'll go by the algorithm, we'll end up with M1. Yes, if you are looking with men oriented. Yes. Okay. And so any other question for this problem?
Yes. If
And
two
we should
men,
have thought all these things before submitting our assignment. We already submitted assignment on this marriage matching.
Yes, yes. Okay, but
Actually, we should have thought before the submitting the assignments.
oh, so this is because this is because these weeks are one week are going bit like that. So your submission dates are now your submission
Yeah, it
dates
is.
are occurring after these uh, before these lectures. But I think that that's fine because like in the NSEM exam, in the last exam, all of these will be coming, right? So you'll be anyway needing, and this is like a revision of your topic. So once you have submitted the assignment, you have basically tried all these. So now you can ask your doubts.
I have one question.
Yes, yes,
If two men have a same preference list,
yes. Okay.
can we have no? Then there won't be a stable matching man oriented or woman oriented.
Uh, that's not necessary. No, that's not. Uh, so by man oriented we just mean that in that by man oriented we are just saying that uh, uh,
Then you
that
have to go for second option.
yes. So
Man is to go for second option.
huh. So it is not necessary. So when you are saying that it is a man oriented matching, it is not that all men are getting their first preference.
Hmm.
So when we are saying some matching is man oriented, it is not the case that all men are getting their first preference. It's just that they,
It depends upon the woman also.
yes, yes. So
I did not saw any example having same preference order in these problems. 3, 4.
say,
You can make
so
you can make problem.
so basically see if we were there, so when we were uh okay, this one, sorry. So when we were there, so here also, like we can, so what is your question? Basically you're saying that you haven't seen any example. You haven't seen any example in which
Having two men can have a same preference order like that M1 have W1, W2, W3, W4. Similarly, any other man can have same order M1,
huh.
W2.
Okay, okay, yes. So see, we'll now our next question is to find the matching. So you see, given any data, we can always find a stable matching. So even if few
Example,
rows
it
are,
is
even
yes.
if some have same preference list, then also we'll be able to find a stable matching. So I think in this, I don't know if in this example. So
Yes, yes,
in this only you can see
yes, yes.
B and C have, so now we'll construct this, so you'll be able to see in this B and C have same preference list, but we will be able to construct a stable matching. Okay. So now our next question is to find a student oriented and university oriented stable matching using the algorithm. So first I want to recall the algorithm. So it's a Gale Shapley algorithm for finding a stable matching. So basically, what is this algorithm saying? So this algorithm that it is defined as men oriented, but if you replace men with women, then it will be women oriented. So it is sufficient to define just one. So suppose we are defining the men oriented algorithm. So what is, so we have this data. Now we want to construct a stable matching. So what do we do is this algorithm will keep on running until all men are engaged. So initially all men are free and all women are free, and this algorithm will keep on going until all men have been matched with some women. So what we do first is that First step is that we start with our M1 and we look at the highest preference of highest preference we look at as highest preference. So now we can have two cases. First of all, the women that is highly preferred by M, she can be free or she can already be engaged. So if she is free, if she is free, that is if she hasn't been assigned any other men, then MW becomes a pair. But so W accepts M, so M is no longer free now. But if W is already, if that woman is already engaged to some men, say M dash, then she decides accordingly. That is, if W prefers M over M dash, then WM becomes engaged and M dash becomes free. But if W prefers M dash over M, then M remains free and the original pair original pair is what we start with. So we'll understand this algorithm better by an example. So so first this is our preference list, and here the two sets are students and university. So first is we want to find a student oriented matching, student oriented stable matching. So we start with student A. So highest preference of A is D university. So at first step A and D becomes AD is one pair. Now this is step 1. Now at second iteration, B, what is the highest preference for B? C. So BC is 1. Now at step 3, CC we see, but C, you see that C prefers C, but C is already engaged. C at third step, little c has highest preference, but C has already been assigned. So now we want to look at, C has already been assigned. So now we look at the other table. So C has two prospective things. So either BC or CC. So what should be in the list? So we see that C prefers C over B. So at third step, BC will be cut, BC will be removed, and instead of BC we'll have C little c. So is this step clear to everybody? BC will be removed. So now we have that. So we have to run this algorithm until all students have been assigned some university. So A has assigned C. Now we go at D. Now D goes to D. But D has already been assigned to A. So now we look at the preference of D. So who will D prefer? So what in fourth step, what is the matching? So BC got cut in the second step. So in the fourth step, now in the third step, the matching that we have is AD and CC. Now we are looking for DD. So we see D prefers D over A. So AD will also get cut and we'll have DD, and CC was already there. Now at fifth step, only now also A and B are both free. So we'll keep on running the algorithm. So now A. So D, since D has already, so now the highest preference of A was D, but A has already proposed to D. So now we'll go to his next preference, that is A. So we'll go to A. And at the sixth step, B has already assigned C. So we go to his next preference, that is B. So we see that the student oriented matching that we are getting is AA, BB, CC and DD. So is this algorithm clear to everybody?
Yes.
Yes, ma'am.
Okay. Okay.
Yes, ma'am.
Okay. So this is the student oriented. What about university oriented? So here you can see. Here you
C
can. Uh,
A
yes. So at first step we have AC. Sorry. AC. Second step we have BD.
C A
Third step we have CA. And at fourth step we have DB. So we see that in all these all are distinct. So they can all so since all have different first preferences, all universities have different first preferences, they are getting their first preferences. So this is university oriented stable matching. So the question that was arised earlier, so you see that here B and C had same preference list, but still we are able to find a stable matching. One of them get their first preference and the other person get their second preference. So is this algorithm clear to everybody?
Yes, ma'am.
Okay. Okay. So now we okay, now we'll do this algorithm for one this matching. So this data basically Sisla. Yeah, okay. So let's find women oriented matching. Okay. So what is our first pair?
W1M4,
W1M4. Okay. What is the second pair?
W2M2,
W2M2. Third pair?
W3 and 4.
take now.
W3M4. But we see that M4 has already been assigned. So what now? We go to the men's preference list. So now if we go to men's preference list, so we have to
M4
dub,
first W6.
so so we have W3M4 and W1M4. We have to choose between these two. So we see that M4 prefers W3 over W1. So third pair is W3M4. And what is the fourth pair? W4M3. So here also you see in this, oh, no, wait. Sorry. So there's some error. So W3 prefers M4. So W1M4 got cut. Now, now W2 is engaged to M2, W3 is engaged to M4. At fourth step, W4 get engaged to M3. Now what about W1? What about W1? W1 has already approached W1 has already approached M4. So we go to the next preference,
M3,
W1 M3. But M3 has already been assigned. So we see at the women's list now. So sorry,
M3,
men's list, and we see M3 prefers W1 over M4. So we can add W1 M3. So we have to cut W4 M3. Now also we haven't exhausted. Now also there is one more women which is free. So we'll look at W4. Now W4 will go to M3. The next preference for W4 is
M1 only, no?
M2. So W4 has already approached M3, but now W4 will approach the next person, M2. Now if W4 is approaching M2, but M2 has already been approached, so we'll compare with M2. So M2 prefers W4 over W2. So this W2 M2 will also got cut. And we are left with W4 M2. So at sixth step also we don't have a stable matching now. Now we look at W2. So W3, W1, W2. W2 has already approached M2. So now W2 will go to M4. But M4 has already been assigned to W3. So we look at the men's list M4, and M4 prefers W2 over W3. So W3 M4 will get cut. Okay. And now at 8th step, okay, W1, W4, W2. Now we look at W3. W3 has already approached M4, and W3 has already approached M4. So now W3 will approach M1, and M1 is free. So we see that this is our stable matching. So our stable matching is W1 M3, W2 M4, W3 M1, and W4 M2. So is this fine? So see, so at each of these steps we were just left with one woman, but we don't directly assign to the person that is left. We go through her to find stable matching. We have to go through her preference list. That we have to first approach the highest rated men which has not been approached before. We cannot directly assign the person that has been left over. So we see, for this case, this is the perfect matching. So is this also clear?
Yes, ma'am.
Okay. Okay. So these were the problems for today. So if you have any doubt, you can ask.
Ma'am, one small doubt.
Yes.
Blocking pair, please, ma'am, explain one more.
Which route?
Blocking pair, madam, please, one explain.
Okay, blocking pair. Yes. So see, uh, so yes. So see, we have this list. We have this list. This is the list of men and this is the list of women. So blocking pair we always define with respect to some matching. So in this case I am taking this as my matching. So my matching is M1W2. Okay. So my matching is this. M1W2, M2, W3, M3W1 and M4W4. And now similarly, if I look at the women's side, W2 goes to M1, W3 goes to M2, W1 goes to M3 and W4 goes to M4. So now we want to see what are the blocking pair. So first of all, if we look at M1W4, M1W4 is not a blocking pair. Why? Because M1 is assigned W2. M1 is assigned W2, but now we are so M1 is assigned W2, but so M1 prefers W2 over W4. Therefore, M1 W4 is not a blocking pair. But we see that M3, if we look at M3 W2, Now, if we look at M3 W2, M3 prefers W2 over W1. So M3 is happy. So basically, for blocking pairs, both of them should be happy. So for M3W2, since for M3W2, M3 is assigned W1, but M3 prefers W2 over W1. So by this new assignment, M3 will be better off. So M3 is better off. Now we look at W2. Is W better off after this new assignment? So we see W2 W2 also prefers M3 over M1. W2 has already been assigned M1, but she prefers M3. Therefore, M3 is also better off by this new assignment. So both M3 and W2 are better off. Therefore, M3 W2 is a blocking pair. But when we were looking at M1 W4, W4 was happy. W4 was better off by this new assignment, but M1 was not better off by this new assignment. So this was not a blocking pair. So for a blocking pair, both of them should be better off by the new assignment. Is the definition now clear?
Okay, ma'am.
Okay. Any other questions? Any other questions?
No, ma'am.
And do you mean
Yeah,
to
sir.
say that all the first preference of men
Hmm.
are blocking here?
So, sorry, what
Do you
is?
mean to say?
Hmm.
Do you mean to say that
Hmm.
all the first preference of men are blocking pair?
For in this example,
Yeah.
so
No, general
in general, what first preferences are no,
of men are blocking
no,
pair.
no, not necessarily. So see here, so not necessarily. So W1 M2. So if in this example only, if you look at W1 M2, W1 M2 is not a blocking pair. First preference of W1 is M2, but M2 W1 is not a blocking pair because M2 has been assigned W. So if you look at W1 M2, M2 prefers W3 over W1. So M2 is not, M2 does not want to change. Therefore, W1 M2 is not a blocking pair. So it's not necessary that the first preferences will come out to be blocking pair. But I am saying that when we are trying to prove stable matching, if there are blocking pairs, they will be coming from they will be coming from these things. The preferences which are, but it is not necessary that all the first preferences are blocking pair. Was this your question? Was this your question? Okay. Any other questions?
That is blocking pair will be different if it is women oriented.
See, it's not more about,
Blocking pair will
it's not about women oriented or men oriented. So when we are looking at matching, the men oriented women oriented matters only when we are trying to find matching through the algorithm. But it's not necessary that if we are that all these stable matchings are either men oriented or women oriented.
The blocking pair depends on a given matching, no?
Yes, yes. So basically blocking pair is defined to see, like we want to see if a matching is stable or not. So if a matching has a blocking pair, then we say that matching is not stable. So blocking pairs are always with respect to some matching. So so when we change the matching, blocking pairs will be different.
When the matching will be unstable,
Yes, yes, yes. If a matching has a blocking, if a match if we matching has blocking pair, so blocking pair was basically, it was not an element of a matching. So blocking pair was a tuple which was not already. So if we were given a matching blocking pair, by blocking pair we were referring to some other assignment other than the matching assignment that have already been done in this M. And then we are looking that if in that particular matching, so if we are given a matching, if we can find a better matching. So see, so when we are saying that something is a blocking pair, so if so why it is so why the matching is not stable? Because if we have a blocking pair, that means that the assignment that we have already done, we can change that assignment to get something in which both the parties will be happy. So they are blocking pairs are defined with respect to some matching, and if we have exhausted, if some matching won't have doesn't have any blocking pair, then that matching is stable.
can we compare this with perfect matching?
So perfect matching, so basically this is not a graph, this is, you see, this is not a graph. But if we want to convert it into a graph, if we, so basically we so best way to do this will be all the men's and all the women's are vertices, and the preferences is some kind of a, so in this you see each man is assigned some women. So basically it is some kind of a complete graph, basically it is some kind of a bipartite, complete bipartite graph, but each edge has some weight. So
Hmm.
matching is so matching is a perfect matching, but stable matching is a special case of those perfect matching. We want those. So maybe stable matching, like matching is so if we considering men as one set and women as one set, this is a complete bipartite graph, and by matching we are basically saying we are looking at a perfect matching of this complete bipartite graph. But when we are saying stable matching, then I think I I don't know yet, like if there's
This
a
can be
analog.
drawn like a line graph, madam.
So
This can be drawn like line graphs.
no, I this line graph as in, so this is just this, right? M1, M2, M3, M4, W1, W2, W3, W4. So each matching basically each match, so if you have this matching M1, W2, M2, W3, M3, W1, and M4, W4. So each matching is kind of giving you a perfect matching for this graph. But stable match, I don't know how can we uh, so matching can be thought of as a perfect matching in this bipartite graph, but if you want to consider stable matching somehow using this graph theoretic technique, then some weights might have to be involved. So matching, you can see matching is basically Matching is giving you a perfect matching. All the matchings are perfect matching here. Okay, so if there are no more questions, then maybe we can end the session and I'll see you next week. Okay, I'll end the session.